or code to express where the stress is a lot. It tends to the red end of the spectrum, and it's not so much. It tends to the blue end of the spectrum. We started with computer-assisted design models, simple one, straight graft with a 90-degree angled smaller graft representing the coronary, and I enlarged it progressively, obtaining these geometries. When put under stress at 200 millimeters of pressure, we obtained these patterns, which somehow resembles what Marco showed us in the last slide. Remember the color code. To make a complex story short and simple, we have a Valsalva configuration on the left with 0.45 megapascal peak stress, and we have a straight graft configuration on the right, which is 0.75 megapascal peak stress. Who the hell cares about what a megapascal is, actually? But it means there is 60% more stress to perform a reimplantation or a Bentel procedure with a straight graft than with a Valsalva graft. Then we moved on to something more complex. We used actual CT scans of patients. We converted them into models. We obtained a normal root, by the way, this is me, a straight graft and a Valsalva graft. And when we use the same pattern of stress, we obtain these images, a normal aorta here, a straight graft Bentel here, and a Valsalva graft Bentel here. It proposes almost the same as predicted by the CAD model. Here is 1.7 megapascal against 2.5 megapascal, which is, again, roughly 50% more stress. So, to end up with the formula, the presence of a straight diaphragm graft increases 1.5 times the stress at the coronary anastomosis. Let's skip to the second focus, the annular aortic ectasia and the leaflet deterioration. We started from this observation. Not all root aneurysms causes damages to the leaflets. There are patients who come to the theater with annular ectasia and have very poor leaflet quality, and patients with sinotubular junction dilatation that have better leaflet quality, more often allowing for a valve-sparing procedure. The hydrodynamic postulate underlying this observation is nothing new. To anyone accustomed to sailing, it's common knowledge that the mainsail, which stands in the wind at a narrow angle, only needs to be replaced once in a decade or so. But when we go to the spinnaker or gennaker, or anyhow a downwind sail which stands, which gets the wind from behind, it has to be changed once in a season. So it's a dramatic difference in stress on the structures. We modeled 4 cases, a normal aorta, a dilated annulus aorta, an aorta with dilated sinotubular junction, and finally, the 4th case, worse of both words. When put under stress and obtaining cross-sectional view, which are familiar to surgeons, we obtain this pattern of stress. This is the normal aorta. You see there almost no stress, just a little bit near the commissure. When we go to a dilated annulus, we obtain this image. The stress dramatically increases on the free margin and even in the belly. When we go to a dilated sinotubular junction configuration, you see it resembles somehow the normal aorta. Yes, there is a bit more stress near the commissure, but not as much as we expected, actually. And finally, the dilatation of both annulus and sinotubular junction gives this result. Somehow, again, worse of both words. When we run the same calculation, considering them from a side view, we obtain this. This is a normal aorta. You see the stress near the commissure, but nothing else. This is dilated annulus, free margin deeply involved, and commissure as well, and belly as well. Dilated sinotubular junction, close to normal aorta. Dilatation of both annulus and sinotubular junction. It's like this. When we go to plot this stress on a normalized arc length, which is an imaginary line connecting the free margin to the commissure, we obtain this. The black line is the normal pattern, which is lowest stress in every condition. Junction loss is the blue line, which has a bit of increase in terms of stress, but not so much. Then we have the red line, which is annular dilatation, and you see it's often the worst possible case. And here we got the combined dilatation, which largely overlaps the annular dilatation, suggesting that it's the dilatation of the annulus that rules the stress on the leaflets. So our net result was that going from this configuration, the normal aorta, to enlargement of the annulus, we multiply the stress on the leaflet by 1.67 times, which is in turn 67% more stress, while going from normal aorta to a loss of sinotubular junction, we just add 14% stress to the leaflets. I thank you for your attention. I leave you with these conclusions. The dilatation of the annulus predicts an increased chance of damaged cusps. So root dilatation without involvement of the annulus increases the chance of a true valve sparing procedure. To sum up, we've been through these two formulas. The Valsalva graft reduces tension at the coronary buttons, and annular ectasia greatly decrease chances of sparing the valve without repairing the leaflets. Thank you.
This work, I am from departments of mechanics and aerospace engineering of Politecnico di Torino, and this work tried to answer to these questions. Does the Valsalva sinuses actually play a role during the systole? The objectives of the present work is ascertaining if the presence of sinuses of Valsalva in the aortic root influences and regulates valve orifice area and modulates transvalvular pressure gradient, and those facts independently from the root compliance. The way in which we test this hypothesis is in an in vitro study in a physical model of the left circulation. Some backgrounds. The well-recognized role of the sinuses of Valsalva are in regulation of closure dynamics of the aortic valve, in diminishing the diastolic stress on leaflets, and in modulation the coronary flow. But let's start in the core of the experiment. The first step was the preparation of the silicon conduits. As you can see on the slide, we prepared two kinds of silicon conduits, both with an inner diameter of 25 millimeters, one with Valsalva sinuses and another one without sinuses. The two samples had the same compliance. Then the second step was the choice of the valve. We chose a Freedom Solo stentless, that is a Sorin Biomedica valve, with an inner diameter of 25 millimeter. The Solo stentless is a pericardial valve, has a soft and pliable tissue and perfect sizing and fitting. In general, those two first samples, in those first two samples, the valve was sutured inside each one of two silicon roots, one with Valsalva sinuses and the other one straight. In detail, in the first sample, we try to recreate the physiological condition with recreating the Valsalva sinuses. So the Freedom Solo was assembled in this Valsalva silicon root with a standard surgical technique with a suture called running style. In the second sample, we abolished the Valsalva sinuses, and as well as before, the Freedom Solo was assembled this time in a straight silicon root with the same standard surgical technique. From this first test, we performed in a pulsatile system. We evaluate the Valsalva sinuses effect on the solo hydrodynamic parameters. The third step was the creation of the hybrid conduits. In this time, those two samples were obtained by substituting the upper part of the silicon conduit with a Valsalva or a straight Dacron graft using the classical remodeling technique. In detail, the first Valsalva, the first replacement was done with Valsalva graft. So the Freedom Solo was first assembled in a Valsalva silicon root. The upper part was cut, and in its place a gel wave Valsalva graft was sutured using the remodeling technique. Also in this case, we follow the same steps. The Freedom Solo was assembled in a straight silicon root. The upper part was cut, and here a gel wave graft was sutured using the classical remodeling technique. With this second test, we evaluate the sinuses effect, the Valsalva sinus effects on the hydrodynamic parameters of the Solo stentless valve. Like we can find after surgical remodeling technique treatment. So we mimic the remodeling surgical technique treatment. Some few words on the pulsatile system that we used. We used a V-vitro super pump system that allows to reproduce the functioning of the left ventricle. You can see on the left some parts of this system, the peripheral resistance, the peripheral compliance, the left ventricle, and the location of the aortic valve. Where there the arrow, we can see the pressure the location of the pressure transducers that are upstream and downstream the valve, and the electromagnetic flow meters that is distally positioned from the valve. So the hemodynamic performance was assessed in terms of cardiac output, transvalvular pressure gradient, effective orifice area calculated from the Collin formula, and the visual inspection. Here comes the results. In the left panel, we can see the Valsalva silicon and the straight silicon configurations. In the right, the Valsalva hybrid and the straight hybrid configuration. And as you can see, when the cardiac output is increased from 5 to 7 liters per minute, an increase in pressure drop is present only in the roots without sinuses. And not also that no marked difference is present within each group with the same root configuration. Here the results in terms of effective orifice area, as well as before, on the left the Valsalva silicon and the straight silicon, on the right the Valsalva hybrid and the straight hybrid. An increase of effective orifice area is present only in the root with Valsalva sinuses, and also in this case there's no marked difference within each group with the same root configurations. From direct visualization, we obtain the same results. In fact, when the cardiac output is increased from 5 to 7 liters per minute, an increase of effective orifice area is present only in the roots with sinuses, and this was independently from the root compliance. So this fact leads to conclude that the presence of sinuses is important in modulating systolic hemodynamics. So we can conclude that although the root compliance is extremely important in the valve opening, it appears also that the presence of sinuses are main actors in allowing a progressive increase in valve opening necessary to avoid an increase of gradient across the valve. This phenomenon could be explained by a dynamic balance of pressure in sinus region induced by lower velocity vortices and the central region of the conduit. And this happened via an increased flow across the valve. Further investigation, well, we ask what actually happens in the sinus region and how the relative portion between the valve sides and the aortic sides influences this behavior. This is a very open topic. So I wish to acknowledge Professor De Paulis for this work and Engineer Umberto Morbiducci from Mechanics and Aerospace Department of Politecnico di Torino and Engineer Edoardo Dell'Amico from Sorin Biomedica in Saluggia, since this work was done in cooperation with Politecnico di Torino and Sorin Biomedica. Thank you for your attention.
Well, when we started our experience in 2002 with the Valsalva graft, we were very curious about this graft because we thought that behind it there was a very simple and effective idea. And after studying the characteristic of this graft, we decided to embrace it for two main reasons. The first one was that there was no need to change the original technique proposed by Dr. Tyrone David that is leading the way in this field. And the second reason that apparently he allowed the reconstruction of the sinus of Valsalva not only from a static point of view, but also probably from a dynamic point of view. What we knew at that time about the mechanical properties of the different grafts utilized for the valve sparing operation was learned from this very well done paper from Ley and Yacoub, and they actually studied by ultrasound the cyclic changes in dimension of the aortic root in different scenarios. This is a root of healthy individuals, and as you can see, it has some compliance at the base. That means that compliance at the annulus. It has some compliance at the sinuses level. It also compliance at the sinotubular junction. This is an aortic root of a patient that underwent remodeling technique by Yacoub. It has some compliance at the base, compliance at the sinuses, and almost no compliance at the sinotubular junction. This is a patient that underwent aortic valve reimplantation by Tyrone David with a straight graft, and he has no compliance at the three levels. And this is how the Valsalva graft is supposed to work. It has no compliance at the base, at the collar. It has some compliance at the sinuses, at the pseudosinuses, no compliance at the sinotubular junction. But if this confirmed upon implantation in real patient, well, the answer is yes, at least in a very short term, and this was demonstrated by Professor De Paulis in 2002. He made an echocardiographic comparison between a patient that underwent aortic valve reimplantation with a Valsalva graft and has 7 healthy individuals. What he found? Well, from a static point of view, he found that the pseudosinuses are bigger than the normal sinuses. So we know that nowadays, and there's no escape from that. Whereas the annulus and the STJ are comparable between surgical group and healthy individuals. But on the other hand, if we look at the root distensibility that is expressed here with % change in radius, we see that the compliance of the Valsalva graft, the pseudosinus, is very similar to the normal aortic root. So at least in a very short term, the compliance of the Valsalva graft look like the compliance of the healthy individual's aortic root. But what happens in the mid and long term? This the question we asked ourselves a few years ago when we decided to start with this study. Actually, we made a comparison by cardiac magnetic resonance between a surgical group of 7 patients that underwent aortic valve reimplantation with a Valsalva and 7 healthy individuals. And most of them were doctors from my hospital. I don't know if that could be considered a bias or not, but the two groups are comparable from each point of view, also from the systolic and diastolic pressure point of view. That could be a real bias. We use a 1.5 Tesla magnetic resonance system equipped with 5-element array surface coils in order to improve the image quality and to provide a larger field of view. Vector-cardiographic gating was used to ensure 100% efficiency in air wave detection and cardio gating, and acquisition were taken during mid-expiratory breath hold in order to minimize artifacts. After acquisition of cardiac standard plane, according to Society of Cardiac Magnetic Resonance, additional steady-state free precession plane were acquired perpendicular to the left ventricle outflow tract in order to obtain, as you can see in figure A and B, two orthogonal planes at the aortic root level, and then an additional SFP images with thickness of 5 millimeters was acquired at the aortic root level, as you see in figure C, and the same image was then acquired at the ascending aorta level. Then for quantitative measure flow, measurement and contour tracing of the vessel data were transmitted online to this software. This is a Canadian software that has a capacity to trace the contour of the aorta automatically, and we actually measured the contour of the aortic sinuses and ascending aorta in healthy individuals, and pseudosinuses and tubular portion of the graph in the study group. And this is how the software follows the changing area during the systodiastolic cycle. This is the measurements. This is an example of a measurement of the pseudosinuses, and you see the number that are changing, and this is the graphical representation of the area calculated every 24 milliseconds that is changing during the cardiac cycle. Well, with the maximum and minimal area and the pulse pressure, we thought to measure some indexes of the aortic stiffness, like the pulsatility, the compliance, distensibility, and elastic modulus. We also thought to measure the area of periaortic fibrosis that always is around the prosthesis after surgery. What we found, well, the mean follow-up was 55.2 months, so it's midterm, I would say. Well, control group, healthy individuals. As you can see, the pulsatility at the aortic root level is slightly higher than the ascending aorta, and this is not significant. Same result for compliance, distensibility, and of course, the other way around for elastic modulus, indicating that ascending aorta is slightly more rigid than the aortic root in healthy individuals. Control group, Valsalva graph, what we found? Well, what we found was that the pulsatility at the pseudosinuses here is much higher than pulsatilities in tubular portion of the graph, and this is significant. Same results were obtained for compliance, distensibility, and of course the other way around for the elastic modulus, indicating that the ascending aorta, that the tubular portion of the graph is much rigid than the pseudosinuses of Valsalva. Well, whereas the elastic modulus changed very little in the ascending aorta, in the tubular portion of the diaphragm, and we already knew this from the study of Baunerschmidt, that showed that the tubular part of the diaphragm has at least a partial loss of the wing castle function, so we already know this data from the literature. When we compare the surgical group and the control group, what we found was that pulsatility of the Valsalva graft at the aortic root was halved when compared to the normal aortic root, and this was significant. Same result for compliance. The compliance of the pseudosinus is about half when compared to the normal aortic root. The same for distensibility, and again, the other way around for the elastic modulus. We also, as I told you, we thought to measure the amount of fibrosis around the graft in order to see if this fibrosis could influence the compliance itself, and we found a high variability among patients with a mean observed value around the aortic root that was 9 square centimeters. When we tried to find a correlation between the periaortic fibrosis and the root compliance, we failed, so that apparently there is no link, there is no relation between the amount of fibrosis and the mechanical properties of the vessel. So what we found was that the mechanical properties of the aorta are significantly different between the surgical group and the control group. But Nevertheless, the aortic root of surgical patient, that is the skirt portion of the graft, seems to have distensibility, pulsatility, and complex approximately halved compared with controls. However, the elastic properties of the pseudosinus are still there after a few years. Indeed, pulsatility, complex, distensibility, and elastic modulus of the skirt are significantly different than those of the tubal part of the graft. This finding seems to confirm that over the years, the Valsalva graft continues to behave like the native aortic root, not only from a static point of view, that is the curvature of the sinus itself, but also from a dynamic point of view, somehow responding to the systodiastolic changes. So it's not surprising that in the contrast group, the elastic changes in the tubal portion of the graft are minimal. And we already know this. We also found a lack of correlation between the periodic fibrosis and the graft mechanical properties, indicating that the inflammatory, apparently, postoperative reaction generated by the graft does not affect in any way its dynamic function. The mechanical properties of the Valsalva graft that seems to be to a certain extent maintained during the midterm could play a role in the durability of the native valve, but of course long-term results are needed in order to confirm this data. Thank you very much for your attention.
Dear Chairman, dear Professor De Paulis, dear ladies and gentlemen. So, when do we do remodeling in a bicuspid aortic valve? In general, we preserve every bicuspid aortic valve in the absence of calcification or valve stenosis. We do the remodeling technique if we have a root dilatation defined by a sinus of more than 42 millimeters to 45 millimeters in TEE, with or without aortic regurgitation. In some rare cases of unfavorable anatomic variants, we do also remodeling in isolated aortic regurgitation. I will come back to that aspect later in my talk. So why do we prefer the remodeling technique? Everybody of you knows the two valve sparing techniques. On the one hand, the remodeling technique, which recreates the sinuses and stabilizes the sinotubular junction. And on the other hand, the reimplantation technique, which additionally stabilizes the aortoventricular junction. We already heard this morning that aortic root distensibility is markedly reduced at all levels of the aortic root after the reimplantation technique, whereas the remodeled valve has almost normal root distensibility. Moreover, we could show in an in vitro model that aortic cusps do touch the aortic wall after the reimplantation technique, and so the cusps are exposed to a higher stress. The different valve opening and closing is very impressively shown in these two video clips. On the left side, the reimplanted valve with a very fast and abrupt opening and closing, and on the right side, the much more uniform and smoother opening and closing of a remodeled valve. I like to show some of our data. This is an analysis we did 3 years ago, and you see that we do both techniques in different valve morphologies like tricuspid, bicuspid, and unicuspid aortic valves, and also in different pathologies like type A dissections. In multivariate analysis, we found that an aortoventricular junction of more than 28 millimeters and an effective height of less than 9 millimeters were significant predictors for late aortic regurgitation. The same factors, plus the use of a pericardial patch, were predictors for reoperation. The operative technique, so remodeling or reimplantation, did not affect the results. Let's come to the anatomic variants of the bicuspid aortic valve. We know that they are not as uniform as generally believed. We have different fusion patterns, where the most frequent is a fusion between the right and the left coronary cusp with about 90%. We also have a difference in degree of fusion from minimal to complete fusion. And what is less recognized is the fact that we also have a variability